My name is Beverly Wolfert, and I wanted to welcome you all to the first ever virtual lab tour. I try to sometimes think of some of the silver linings to this entire pandemic, and I'm hoping this might be one of them, that we have the opportunity to bring more people with us along to visit to one of our incredible research projects that spans 2 labs at NYU and MSK. So I'm really glad that you could all join us to get to know more about this incredible project that Tina's Wish is funding. Just 2 pieces of housekeeping. One, we wanted to let you know that the session is being recorded just so that we can use it in the future as well. And the second thing I wanted to mention, I'm sure most of you are familiar with Zoom, but it's probably best if you can be in speaker view so that you can see the person that's speaking. Otherwise, feel free to go into gallery view and see all of your friends and colleagues that have joined us as well this morning. I also wanted to acknowledge this morning 3 families that have joined us that have sadly lost family members to ovarian cancer this year. And really, it's in memory of your loved ones and in memory of Tina Brosman that we continue to do the work we do every day so that we can begin to allow women to know early and hopefully know hope so that they do have a fighting chance against the disease. I've often heard that Tina Brosman would say that she wasn't angry for having the disease, she just wished she had had a fighting chance. And that's what we aim to give all women, is the opportunity to know early and hopefully know hope. If I don't have a chance at the end of the program, I do just want to wish everyone very happy holiday season. I hope you stay healthy and that we all have the opportunity to convene in person at some point in 2021. I'd like now to turn the program over to Sherri Toub, who will be our moderator for this program.
Thanks so much for that introduction, Beverly. In addition to having the distinct pleasure of serving on the Tina's Wish Leadership Council, I'm certainly honored to have been asked to moderate this morning's panel. To start, I must say that it's great to see so many familiar faces and to meet others, albeit virtually, who are key supporters of the truly critical mission of Tina's Wish. This is an organization that I hold near and dear to my heart, in large part because my favorite person in the whole world, my grandmother Rose, was taken from me by ovarian cancer that was detected way too late. So before I introduce the stars of the show, for those I don't already know, I'm Sherri Toub, and I'm a partner at Kekst, which is a global strategic communications firm. In a nutshell, we help companies engage effectively with their stakeholders at pivotal inflection points and moments of transformation. Given what I do for a living, it's not at all lost on me that today's panelists are leading the charge on a project that is truly transformational and at its own critical juncture. During our time together this morning, we're going to hear about the absolutely life-changing work of 2 of Tina's Wishes researchers, Dr. Dan Heller from Memorial Sloan Kettering Cancer Center and Dr. Doug Levine from NYU's Perlmutter Cancer Center. As the doctors will share, they are collaborating to develop an implantable nanosensor that can detect ovarian cancer in its early stages. And as the Tina's Wish mantra we all know goes, and as Beverly just mentioned, when it comes to this form of cancer, we know we can know hope if we know early. So before we dive in, just a few administrative matters to get out of the way. I want to remind everyone in the audience to please feel free to type questions into the chat box during the course of our chat. And as they cross your mind, no need to wait until the end of the discussion. In that respect, I'm told that by default, the chat is visible to everyone. So if you prefer to direct your question to me only, so your name remains anonymous, simply choose Sherri Toub in the chat drop down before typing in your question. And with about 5 to 10 minutes before we conclude, we'll address questions via the chat first. For those who prefer to ask their questions live, that's great too. You can use the raise hand feature at the conclusion of the panel portion, and I'll call on you to ask your question directly to the doctors. We know everyone has a busy day ahead, so we'll look to wrap the session up by 9:15 as promised. So without further ado, welcome Dr. Heller and Dr. Levine. Do you want to wave for our, there we go. There we go.
Good morning, happy to be here. Thanks for everyone for joining, appreciate it.
Great. I think it goes without saying that everyone who joined is very interested in learning about the project, where it's at, where it's going, and its extremely promising path forward. Before we get into details, let's get into some basics, particularly for those of us on the call without an MD or a PhD attached to our names. So Dr. Heller, if we could start with you first. I mentioned earlier that you're developing an implantable nanosensor. Can you explain in layman's terms what nanotechnology is, and then share with us how you're applying it to ovarian cancer early detection?
Thanks much, Sherri, and good to see you all on here. So my laboratory focuses on engineering new technologies for the detection and treatment of cancer. And so, and the basis of what we do is nanomaterials. So nanotechnologies, nano just means a billionth, and so really small materials. And we're developing sensors in our lab, focused using a material called carbon nanotubes. And I actually have a 3D printed carbon nanotube here that I can show. This is basically just a tube made out of 100% carbon, and the size of this thing is such that if you could shrink it down about 100,000 times, you would get, if you shrunk down hair, a strand of hair 100,000 times, you would get to the size of one of these in real life. So that's how small these things are. These are about 1 nanometer in diameter, and these tubes are unique because they give off light in the infrared range of the spectrum, or the near infrared range, which is a range of light that can really pass through tissues. And so with these, we can make implantable devices where we can get information into the body and out of the body. And these also have unique properties in that we can make sensors out of these that are extremely sensitive. So the fluorescence, the light that we can get from these things that can pass through the body, can be changed based on events where, say, a biomarker of ovarian cancer binds near the surface of these things, and that could change the properties of the light so that we can measure it. So we basically have a material that allows us to make a sensor that can transmit information out of the body. And I wanted to give you a real lab tour today, and if this was a non-virtual event, this would be a lab tour. But fortunately, the postdoctoral researcher in my lab who's been developing these technologies is in the lab right now, and he can show you a very short virtual tour, if that sounds like, Sherri, what we can do right now.
Absolutely.
Hi, Zvi.
Hello everyone. Welcome to our lab, the Heller Lab, and I'm Zvi, and I'm very happy to be here. And I wanted to give you a glimpse of what we are doing and how the sensor world look like. So first of all, as Dan mentioned, the nanotube, I will just flip my camera to the front one. Our solution starts with a very black solution, 100% carbon, as Dan mentioned, you can see here. Although it's very black, when you turn off the light, basically, you will see very nice things. And the definition or the term that I'm using here is called fluorescence. So for instance, if you are lightning or a shining light on these materials, and here is like UV light, okay, you will get very nice colors, okay? And this is depends on the material or the substance that you are shining light at. So this material shines shines light in different colors, and it's very interesting. And also the nanotubes. So basically the nanotubes have, and I will share the screen here, have different properties. So if you look at this map, for instance, you see that all the peaks, all the red areas are different populations or species of nanotube. So imagine that it shines in pink and gray and green and red and blue. But in this type of substance, they are shining light in the near infrared, meaning in the region that we can't see it in our eyes. So we have a special instrument, a custom-made microscope that Dan and others have been optimizing in the past several years. And basically what you see here are the peaks of light that the nanotubes emits. And basically each peak here is reflecting a certain species here of the nanotubes. And for instance, if I want to shine light, you can see here a very nice, it's a little bit dark there, but you can see the teal light, okay? It will excite different populations that will emit light in different peaks, but we can definitely play with these colors and light, and basically we can switch to any colors that we want, okay? And the idea is eventually, I'm turning on the light again, the idea is to implant the sensor inside a very small implant, okay? Do you see the membrane that I'm holding? It's about 4 millimeters wide and about 2 centimeters long, but I can make it shorter and shorter as much as I need. So the idea is to implant this device into the uterus and then shine light with a fiber optic and get a very good readout about the light of the nanotubes. Now, the light of the nanotubes is very correlating with the environment, because the surface of nanotubes is very, very sensitive to the surroundings. And here in ovarian cancer, we want to monitor different biomarkers that the cancer or the tumor secreted outside the environment. For our experiments, we are using currently mice to show the proof of concept and to optimize the technology. So here is, for instance, because I'm not allowed to bring mice from the animal facility currently, this is the phantom mouse that we are using, okay? And basically this is the laser, and the idea is to implant the membrane or the device inside the mouse body and shine light on the membrane and get the readouts in terms of the peaks. Now, if the peaks is changing, getting higher, lower, moving right or left, it's shifting, then we know that the nanotubes or the sensor are responding. And I just want to give you to give you some clue about how does it look like in the real life. So you can see here, this is a real mouse, and this is the implant inside its belly, okay? Because the mouse body is very, very small. And you see that in the near infrared region above what we can see, basically near infrared region it's very commonly used in your TV, for instance, in your remote control, in your AC, and etc. And for us, it's opened a new range of different colors. So here you can see a very black mouse. It's not because it's black, actually it's white, but in the near infrared, it's black. But you can see that the nanotubes or the sensor is very, very bright. It's like a torch. And basically this is the mouse, okay? It is white, but you can see the light when you shine in a specific laser, you can actually see the light. And by focusing on the signal from the nanotubes, you can see the peaks. Here are the peaks of the nanotubes. And by correlating the peaks with the concentration or levels of the different biomarkers, then we can actually set a threshold where when we're passing the threshold, we can say that there is a high chance of progression of the tumor. So this is just a glimpse of what we are doing here. by developing this implantable sensor.
Thanks so much, V. And thanks for making us a quite impressive virtual lab tour. That so he's in the optics room of my lab right now. And
My pleasure.
And thanks so much, V. That was excellent. So he gave you a sense of kind of what we're looking at every day in our lab, and he was showing how really a little bit of a mock-up about how we got our first data in an animal, where we basically were able to shoot light at an animal that had cancer, and we were able to detect the markers of ovarian cancer, one of the main biomarkers of ovarian cancer, from inside a mouse by just shooting light at it, by basically like a flashlight.
Well, even that demonstration makes clear that this this job that you all have undertaken is not the role or the job of one individual. And collaboration is in so many fields, including in the medical research field, key. Can you share with us a little bit about how the collaboration between you and Dr. Levine began?
Absolutely, and I can definitely answer questions. I saw some in the chat about a little bit more about how this is going to work, and actually Dr. Levine is going to tell you a little bit more. So my lab, I started at Memorial Sloan Kettering in 2012, and realizing that my lab is not necessarily a cancer biology lab, but an engineering lab to develop new technologies to detect, to research, and to treat cancer. And one of these main technologies is the sensor technology. And so when I met Dr. Levine, I really met him literally I think in the lobby of this building. And he said, we really need a way to detect ovarian cancer early. We need a sensor. And I was super excited. I said, but that's exactly what we do. We make sensors, and we want to, and I came to Sloan Kettering. I came to a biomedical research institution like this because I wanted to use my skills as an engineer to really to address really hard problems and really important problems. And so really meeting Dr. Levine and him explaining this and starting this collaboration really, I think, made magic happen, because he really took me and our lab and said, this is a really big problem. You should be focusing on this. And now multiple people in my lab are focused on on ovarian cancer. Z and also another postdoctoral researcher in my lab, Mijin, and several others are really focused now on this problem because of meeting Doug. So it really kind of, we had this, we're engineers and we could go after many problems, but meeting Doug is really what got us focused and into the fold and working with ovarian cancer and with Tina's Wish.
Dan, since you mentioned my name, I'd like 30 seconds of rebuttal, please. Dan's completely correct. It's been a pleasure to work with Dan, but I just want to say, he reminded me that, we've had a great collaboration with his lab and my lab, and we're making great progress. But actually through Tina's Wish, they've also heard about this work, and Dan is now collaborating with people at the University of Pennsylvania and Johns Hopkins, where they're also using this technology to investigate sort of a tangential angle of the nanosensors for other applications. And so, once you build something, it really grows. And through Tina's Wish and some other things that Dan is doing and some things that we're doing, but through Tina's Wish, we've really been able to expand that critical mass to other people who now know about the technology and capitalize on that. And before I forget, Dan, I loved your example of how you take carbon molecules and turn them into a nanotube, to help the funding of our research. Can you turn that into a diamond also?
I'd love to, but no, I like a rebuttal to rebuttal. No, that's exactly right. Really working with Tina's Wish, I met so many amazing researchers in the ovarian cancer space. And actually, there's people here at Sloan Kettering that I don't think I would have met if it weren't for Tina's Wish, that are other ovarian cancer researchers that we're working now very closely on multiple projects, all for the detection of ovarian cancer. So it really is to the credit of Tina's Wish and Doug to bring this together and really kind of allow us to shine a light on cancer.
Yeah,
Really.
well, it sounds like a bit of kismet there with the two of you, and then liaising with Tina's wish to bring it all to fruition. Dr. Levine, when you think about this project from its inception to where you're at now, what have been some of the most exciting developments or one of the aha moments that you can share with us?
Yeah, well, to answer a different question, it's interesting that, just to keep things, contemporary, but it's interesting. We actually started working with Lockheed Martin, the defense contractor, just before Dan came, because they had some technology that also was going to do nanosensing, but it really didn't work out. We actually had to have Dan be recruited to MSK so we could be more successful than working with one of the largest defense, contracting companies. But I'd say there are two aha moments. One was the major discovery that most ovarian cancers begin at the end of the fallopian tube. We and others have been working on this for about 15 years. We continue to publish papers to refine and establish the relationship between the fallopian tube and the origins of ovarian cancer. We've had 2 or 3 papers come out just in the past year in journals such as Cancer Discovery and other things with our lab and other labs, showing that. So that's the first aha moment, is that ovarian cancer is not really ovarian cancer. As many of you have heard me say before, it's cancer on the ovary, but not cancer of the ovary. And we're not going to change the name. It's still ovarian cancer, but it begins at the end of the fallopian tube. And then the next aha moment was like, well, the fallopian tubes are connected to the inside of the uterus. How can we capitalize on that? And we did some early studies measuring protein-based biomarkers on the inside of the uterus. And we believe they're expressed 10 times or more at a 10-fold higher concentration inside the uterus than in the bloodstream. And so for many years, people have been trying to use CA-125, which is a tumor marker that we can measure in the blood. People have been trying to use that as an early detection marker, which is not its intention. And then we discovered that we can actually get better sensitivity, so to speak, inside the uterus, which is where a lot of these studies and other studies have followed from. So you've heard about our nanosensing technology here. Other people around the country and the world are doing fluid sampling from the inside of the uterus, are measuring DNA fragments from the inside of the uterus and from pap smears and other sorts of things. And so knowing that as you get closer to the source, you're going to have what we call a higher signal to noise ratio. That was sort of the second aha moment.
Yeah,
so to speak.
And when you think about where you're going from here, what are the next immediate milestones, and what do you need? And I ask that question broadly because it can be from a financial perspective or in terms of resources or the like to reach those milestones.
Yeah, so that's a good point. And before we run out of time, I want to also have a little show and tell, just to be fair, since again, my 30 seconds. So I'm taking out my background. You can see that behind the mask, but so some people ask about where the device goes. And so this is actually an IUD, for those of you who don't know what it looks like. And it's about 2 centimeters long and 3 millimeters wide. And so that carbon nanotube that you heard would fit nicely inside this IUD. This is red because it's not for human use. Although someone gave me one once to try to put inside of a human, but we saw that it was red. So it's normally white, so the white ones go inside humans, but this part in the middle is a cartridge that normally secretes progesterone hormone, which helps with contraception. And so we're gonna actually swap out that cartridge and put in Dan and Zvi's membrane into that area where it can sense biomarkers inside the uterus. And so someone else asked, does it go inside the uterine wall? I know the lighting's not great here, but this is a uterus that I'm trying to orient for you. You can see the uterus, and basically, I need 2 hands for a second. So I can load this IUD into my IUD applicator, and I can take this model of a uterus. It's not a real uterus, it's a model of a uterus because the uterus is not purple, although NYU colors are purple, so that's appropriate. And then I can take the IUD, and you can see here how we insert it, trying to get the light here, sorry. Insert it into the uterus, it goes almost up to the top. We then deploy what we call the arms. Let me get that light back for you. And then we put it all the way to the top of the uterus. And then basically this model is not quite as easy to use as a human. We basically withdraw the applicator and the IUD essentially stays inside the uterus. It doesn't actually fall out as it's doing this model. And so keeping the IUD, it can then stay inside the uterus for up to 5 years is what an IUD does. And then you can see this IUD device has some strings. These are a material called polystyrene, but Dan can actually swap these out for fiber optic cables. And so this device, these strings would then sit in the top of the vagina, and we can actually interrogate that with a very non-painful probe that can actually be also done at home. So it could be self measurements, and we can use that as a way to measure the biomarkers on the IUD. And so that's the long-term goal. Zvi showed you how we can measure this in mice, and that's wonderful, but we're very good at curing mice. We're not so good at curing and detecting things in humans. And so we now have submitted a protocol to our institutional review board in order to take the device and put it into women who are already having a hysterectomy, already having the uterus taken out. So we're going to do a proof of principle just to show that in addition to the mice, we can actually detect the biomarkers in a human environment, such as the human uterus. And I expect that protocol to be approved probably not quite by the end of the year, but in the very early part of the first quarter of next year. Once it's approved, we're then gonna measure the biomarkers in 10 women with cancer and 10 women, 10 women who are cancer-free or have no evidence of cancer. And we're gonna see if these wavelength shifts that Zvi showed you how they light up, but it turns out that they light up at different intensities, which is not that maybe the technical correct word, it's different wavelengths, but they light up basically at different intensities, whether or not the nanosensor detects the biomarker, which in this case is HE4, which is an ovarian cancer biomarker that we're starting with. And down the road, we can change it to measure CA125, which Dan is working on. And ultimately, we can have multiple biomarkers go into the nanosensor. And so we're working on the human subjects review. We think we know how to do this. We're only limited by time and money because we all have other jobs that are very time consuming. And so this is one of many things that we work on. And we all have people who work with us who we have to pay salaries. And so the more money we have to do this research, the more progress we make. And that's really true for all biomedical research. And we spend half of our time writing papers and grants so we can actually do the research that we love and enjoy and help with the mission.
What do you, in terms of the clinical trial process, and then for either one of you, when women could potentially see this early screen in their doctor's office, is there any sense of timing and priorities in terms of which women would be able to take advantage of this advice, at least in the early days?
So unfortunately, there won't be early days for that purpose. This is a very difficult project. You know, we don't have, fortunately, we don't have as well, maybe I'm gonna say this wrong, but anyway, it's not COVID where we could put 30,000 women on a trial in 3 months. The first thing we have to do is prove that it works. Second thing we have to do is prove that that our form factor is tolerable. So we have safety and efficacy. We do efficacy first because people are already having surgery, so there's no safety issue there. Then we do it with people who aren't having surgery to make sure it's safe. Then we have to do a trial to make sure it actually works in the population. And that's a big trial. And since ovarian cancer is actually a rare tumor with only about 22,000 cases per year, and of course, we would be doing this in high-risk people who don't have cancer. We have to monitor them, et cetera. It's a large trial that takes a number of years. And so unfortunately, the actual, you know, when this will be ready for prime time / commercialization, we're probably talking 5 to 10 years, but probably in 2 or 3 years, we'll have some intermediate results, which show that this is as exciting and works as well as we think it will.
That's incredible. And could the IUD that you've been, and actually I'm just going to address some of the questions as they pop up because they dovetail nicely with your remarks as opposed to waiting till the very end. But could the IUD that's being used for early detection, as you described, be also used for contraception? So it's basically serving two purposes?
Absolutely. So the funny thing and the good thing about working with teams is Dan and I were focused on this biosensor, and we were presenting this to some venture capital people. We started a company to try to commercialize this and take it further, et cetera. And they asked us that same question. We're like, well, we hadn't really thought about that because that wasn't really our focus, but absolutely, it's going to have the same form factor. You know, we're modeling it after an IUD because the IUD is FDA approved. It's a well-established, you know, mechanism. So there's no reason why it wouldn't serve both purposes. There are other types of IUDs that don't secrete hormones and still provide effective contraception. So certainly that would be a very easy future development to do.
Yeah. And in terms of doing that, are there any, you talked about the aha moments, and either one of you can take this question. But one of the biggest challenges or obstacles you faced, and how does that, lead us to where we're going next with the stages of the project?
On the clinical side, I'll just quick answer and let Dan give his answer. But on a clinical side, it's basically regulatory. So it sounds easy to actually enroll 20 patients, but we need to get IRB approval. They have many questions. We worry about informed consent, of course, patient safety, and then we need people. We need someone to talk to all the patients, to make sure patients understand what we're doing, make sure they don't think we're really doing, terrible experiments on people, which is a legitimate concern. We have to, have people complete paperwork, sign permission forms, create permission forms, log all the data. It's just labor intensive. And so it's challenging just to get even a simple clinical trial done in this environment, which is not a bad regulatory environment. That's what it is, to balance patient safety and progress. It's a lot of work. It takes a lot of time. Dan?
Yeah, so we need to really have more people in the lab doing this at one time. I think Zvi could use a few people working under him. I think he would be very happy with that. So in that case, basically more people trying more things kind of makes science work. So in some respects, it's just being able to pay for more studies, and then to also be able to pay to get those studies accelerated to the clinic, in what Dr. Levine said, where we really need to be able to one, have enough patients to try this on, but also to be able to bridge all of the regulatory issues going to be able to do these trials. So but primarily right now, it's just being able to have enough Zvi's in the lab to do this work.
We can't have the mice. We can't have the mice assist Zvi in his.
I'm sure he would take them as assistants any day if they could just shoot lasers and things like that.
And just to add on that, our 20 patient study will probably take us, about 2 years to do here. But if we wanted to have more patients or make more progress, we'd open it at multiple centers. And then so everything we're doing here has to be multiplied by whatever number of centers we want to have it done. And then if you have multi-center trials, you then need a coordinating center, which is also just added, logistics that all just are challenging.
Yeah. And can women volunteer to be part of the clinical trial? And if so, how would they even go about getting involved?
They can't really do it, I think, from the way you're, sort of asking. We're going to ask volunteers.
Like
No, I know, but the way you're, in that manner that you're asking about, which I understand, the way they can volunteer is when we have people who are having surgery, we're going to ask them if, as part of the surgery, can we also do this minor additional thing, and hopefully they'll say yes. And so we will be asking for women to volunteer, but you can't really come in to volunteer. You can't even, I suppose you probably could come here for your hysterectomy if you needed one and really wanted to volunteer, but we have plenty of people who unfortunately need to have hysterectomies, and that will be our population that we'll do for the first couple of studies. And so we sort of have enough, that's not a problem, for better or worse. We have enough people who need surgery that we have that patient population, and our patients are very altruistic and do participate in our research almost all the time.
And so the way that would work if someone was having a hysterectomy but did and had ovarian cancer is that you would implant it just for a short period of time to know if your device works without any additional risks involved.
Right. So there's 3 steps. So step 1 is we're actually going to not get patient's permission, which is why we're doing it this way. Once the uterus is out of the patient and about to go to pathology, we're going to interrogate the inside of the uterus. So it's already out of the patient. We don't even come in any contact with the patient, just the specimen. And that's step 1. Step 2, with patient's permission, is just before the operation begins, when they're asleep, we're going to implant it. It takes around an hour to do a hysterectomy. So we'll implant it for an hour while the hysterectomy is being performed. Just before it's completed, we'll take it out, and then we'll have a second measurement where it's actually, the biospecimen was in, the biosensor was in a patient. So we need patient's permission for that. And then the third step is we're gonna place it in the office like an IUD about a week or 2 before their scheduled surgery. And then of course we have informed consent to do that as well. So those are our first 3 small scale pilot studies. Once we get to that point, then we're ready to see if it actually works in the ovarian cancer population or some similar type of population.
Got it. I think maybe we have time and I can take 1 or 2 more questions. So let me just check the chat and let's try to take 2. The first is, why has the early detection of ovarian cancer lagged behind other cancers exclusively focused on women?
I guess I'll probably take that. It's hard to detect cancer in the ovary and many other organs like the pancreas and like, for example, the small intestine, because they're deep within the body. So the cancers where we have highly successful screening programs are cancers where we can get access to those organs. So you think of a pap smear, well, you have a pelvic exam at your gynecologist's office, we can see the cervix and take a sample of it. You think of a mammogram, you know, we can do an x-ray basically right of the breast. It's right there for us to interrogate and we can see very good things. We can't do really an x-ray or a mammogram of the ovaries. We did have a researcher who was looking at doing MRIs of the ovaries, you know, early days there. And then a colonoscopy, we can look inside of your colon because we have access, not, you know, people have, doctors have access to your colon. If you let them have access to your colon, you could put a scope in there. People have thought about putting a scope onto the ovaries. There was someone here at NYU about 15 years ago who tried to do the ovarian pap test where he was actually putting a camera into people to do a pap smear of the ovary itself. You know, 1, that probably wouldn't work nowadays because it doesn't begin in the ovaries, but 2, you need anesthesia. You know, there are much more risks with putting a camera into your belly than a camera into your colon. So those are highly successful screening areas. Pancreatic cancer has been difficult because we can't do that also. We actually can look into the stomach with the scope, which is really close to the pancreas. And so that's being looked at now as a screening method, but it does require an endoscopy, which is a bit more invasive than either a pap smear or a mammogram.
Yeah. So essentially we're relying on the 2 of you. So keep up the good work. I'm going to take 1 last question and then a few closing remarks so we can end by 9:15 as promised. Is there a way to involve other gynecologic surgeon specialists? Yes. In other parts of the country to include their patients in the early study?
Right. So we have a very tight network of professionals across the country. There's probably less than 1,500 board certified GYN oncologists. About half of us are academics. That's less than 1,000. I probably know half of those people personally and have their emails and know the other 25% at conferences, et cetera. So we work very closely together. We really don't compete with each other except slightly in New York City because there's too many GYN oncologists in New York City and not enough in the rest of the country. So we collaborate, and when we need to do a multi-center study, we do that. As I mentioned, Dan's working with people at Penn and Hopkins and maybe other centers I'm not aware of. I work with people at Pittsburgh and Cedars-Sinai and North Carolina, all over the country. So we collaborate closely, and whenever it makes sense, we'll reach out to people. If we need a bigger study, we'll reach out to people. We just finished a 10-center study on taking out fallopian tubes called the WISP study. We finished another 10-center study about doing a pap smear basically of the inside of the fallopian tube that's completed now. So we have a very tight network, which is great. We do a lot of team science, and we're probably more successful, however you define that, than we would be without working together closely. Dan, who else do you work with besides those people?
That's most of them. People at Dana-Farber Cancer Center in Boston,
right?
And then other people here at MSK.
Actually, your Dana-Farber collaboration, you're developing some microfluidic devices that also grew out of Tina's wish. Yep. And that's also very promising.
Yeah, actually, at Tina's wish medical, science symposium where we all talked about our work. I got together with one of the investigators at Dana-Farber, who's a Tina's wish funded researcher, and we came up with an idea, and that's actually a patch to put on the skin. And for detection. So that's and that's been really exciting.
Yeah, and I know we're running out of time. The whole cool thing about Dan's technology is it allows something to stay in a local tissue environment for a prolonged period of time. So his patch or our IUD, it sits there and it can accumulate these very rare biomarkers, whereas most other people are working on a blood test where you measure one thing at one point in time, or you do it at multiple time points every 6 months or whatever. But this stays in the local area as an implant, a small implant, and it can measure things continuously, which is really a huge value added to this type of technology.
That's great. And I think we're all very thankful for the work you're doing. We're obviously all very thankful for Tina's wish and Tina's personal mission. And thankful to all of you for attending our first ever virtual researcher roundtable. Thank you to both of you for your important work. We are very appreciative and encourage the continued support of the research you're doing, in addition to the research that other of those funded by Tina's Wish are doing. And on that note, I understand Michelle will be following up with some of you with more information. And I believe today's conversation was recorded, so we'll be providing a link to the extent that any friends, family members weren't able to join. In terms of what's next on the agenda, Tina's Wish plans to feature a researcher roundtable each quarter. So stay tuned early next year for details on the next one. And one last thing before we go, I wanted to mention a new initiative that Tina's Wish is kicking off in the new year. The Empower Her series, Empower Her, H-E-R, capitalized at the end, will be a series of 30 to 40-minute virtual webisodes to educate and empower women in relation to their gynecologic health. Stay tuned for details about the first episode, which will be called Gynecologic Cancers, Facts and Differences, airing at the end of January. To wrap, here's hope to everyone's having a great and safe day. Stay connected to Tina's Wish and to each other, and be well. Thank you all.